Let's give the Simon's Colloquium here in this beautiful new building. I will start fairly elementary, so I hope not to offend the experts. What is a wave equation? So imagine you take a string, this being the x-axis, and your displacement, uxt, and you can imagine this violin string, guitar string consists of small pieces of mass, and you write down Newton's law for each of them. So you have F is ma. So as mathematicians, we said m is 1. No further problem with that. And A would be utt. And the force, quite logically, should be the curvature of your graph there, the graph u of x. If the curvature is negative, it should act as a restorative force pointing down. Positive should bring you back up. And this is indeed the wave equation in one dimension in d dimensions. So this x in Rd. Think of a drum. D would be 2.
Gravity?
I'm sorry? Gravity? No.
Symmetric, right?
Gravity is irrelevant to the string.
Yeah, but so then it should be symmetric. So is that sort of?
It's a force pulling the thing back.
It's just the tension of the string. The tension of the string. It's like a violin string or guitar string.
You have some nonlinear terms, but this is the linearization for small displacement.
Everything linear. Yes. So if you make this, if you try to break your string, the displacement is very strong. Nonlinear effects take over. None of this applies. So this is very important that this is brought up here, because here the wave equation appears as an absolute model. It's unrealistic, perhaps, that a string behaves like that, but we will see that. No, because positive.
It's pulled up. The curvature. If it's
The sign works?
yeah.
Yes.
Haven't you reflect on a guitar string? You notice that it pulls back for both sides, right?
So here the curvature is positive, it would bring you back up. Here the curvature is negative, pushes you down.
Think of it as a series of the springs put together.
Oh, you as a sign. Okay.
You as a sign.
You as a sign. Okay.
So this displacement, this is you.
Sorry.
So this is the famous wave equation, and in d equals 1 for the string, we can solve it explicitly. And D'Alembert not only wrote this down, I think, about 300 years ago, but he solved it too in one dimension. You observe that if Cauchy didn't exist at the time, today we call it the Cauchy problem. So ut equals 0. You start with your initial elongation, and you start with an initial velocity. Let's call them f and g, the second order problem. You have two initial conditions. D'Alembert observed something very neat. Before I write down what he observed, I should tell you how he observed it. Because in 1D, this equation you can write as dt squared minus dx squared, u is 0. And then he observed this. And so imagine I were a lazy undergraduate. Maybe there are no lazy undergrads. I'll just assume for the sake of argument I am a lazy undergrad, perhaps the only one. I would look for the kernel of this product by looking for the kernel of this separately and the kernel of that separately. All right? And you immediately see that if you just look at the kernel of this separately, you obtain that, and we know how to solve that, right? Because u at time t position x would be f of t minus x, right? If I did this correctly, you plug it in, then you see it solves it. But, so this was my first lazy attempt of finding the kernel of this product. Then you find the kernel of this, you reverse the sign. And then we should just take an average. All right? So what D'Alembert observed is that because of this factorization, and of course, I'm free to change the sign in here. You have that. And if you throw in G, you will have this. So this is the famous D'Alembert formula. It gives you all solutions of this equation. Of course, if we want to be picky, we would have to start talking about regularity for which f and g. Notice that for this to be a solution, this needs to be C2, but let's ignore such issues, otherwise we have to talk about weak solutions. But this is the famous D'Alembert formula. In terms of a picture, imagine you turn off G, you only have F. Then how does the wave propagate? It will propagate half of this profile, and this is not half, forgive the lousy picture, will move to the left, the other half will move to the right. All right? And again, this is not a good picture for many reasons. The distance from this profile should be the same, right? Now, what happens in higher dimensions? In higher dimensions, you cannot get away this cheaply, and wave phenomena are more interesting and more complicated. So, in 3D, we can again look at this, and let me now put 0 here, and the initial velocity is g. Then it was observed past D'Alembert in the 19th century, I think by Kirchhoff, that to solve this equation you have to do the following thing. If you sit at x, you draw a sphere of radius t, do this, all right? And you average g over this, and you multiply by time. So the solution formula is utx is t slash ts2 g of x plus y sigma dy, where sigma is the Euclidean measure of the sphere, and the slash means divide by the measure of the sphere, and then multiply by t. If you write this out, it becomes 1 over 4 pi t integral over S2 ts2 g of x plus y sigma dy. Now, to prove this, you observe something clever. In hindsight, it's always easier to guess that this is the right thing to do. You don't look at u, you look at r times u, where r is the radius, the length of x. And you observe that you then obtain a one-dimensional wave equation, and you come back here. That's one way to do it. Another way is to use the Fourier transform. But be it as it may, this is a very nice result. And how to interpret it? Well, for one thing, you see as time becomes large, in stark contrast to one dimension where nothing decays. It's just pure propagation. But here you will have decay. So it's a nice exercise in multivariable calculus to check that the L infinity norm of your wave decays like this. So this is in R3, I remind you. This is the decay of a free wave in 3 dimensions, like 1 for t. 3 space dimensions, time. So you can also write R1 plus 3tx. Okay? Minkowski space. But so x is in R3 here. And so how do you prove this? Well, obviously you have to estimate the size of this integral. And you can actually, so it's a clever trick, you can use the divergence theorem, the Gauss theorem from multivariable calculus to convert this to an integral of the ball. You do a Sobolev embedding, you get this. So it's a very nice exercise. If you throw f back in here, then for this decay, all you have to do is you put a second derivative, f in L1. Now, let's...
Huygens.
Yes. You're taking the words out. Also, this Kirchhoff formula, let's try and draw another picture here, which is a challenge because I now will try to go into 3 plus 1 dimension, this being R3. So if you start with a wave that's localized here to, say, the unit ball or some other ball, some compact set, how will this initial disturbance propagate through space and time? Well, it will propagate, according to the Kirchhoff formula, like this. You see? So fixed time slices are copies of R3, and the wave will live on a neighborhood which are just dilated spheres S2. And the width of this is the width of the support of the initial disturbance. And this is precisely the Huygens Principle that was mentioned a moment ago. So to say this yet differently, if you start with a light flash at the origin and you sit here, then this will propagate as we all expect. Wave fronts, you will see the wavefront when it hits you, which is exactly the time equaling your distance to the origin. You will never see it again. This is what you get from this Kirchhoff formula. In 2 dimensions, the situation is not quite like that. You don't get such an integral over a surface. You get the integral over disk, but there is a weight that favors the boundary. Okay? And this you know from throwing a stone into a lake. There will be wavefronts propagating. Where the stone dropped, the waves will decay, and there will be a front that remains, that carries the energy, so to speak. So since I just used the word energy, I should point out another fact. Over lunch, we were joking how maybe it's true. PDE is integration by parts, so let's integrate by parts. Okay. There is a conserved energy, so the wave equation is Hamiltonian. You can do this in any dimension. If you compute the time derivative, you will find this, where box u is shorthand for utt minus Laplacian u. All right? So this is 0, just by integration by parts. So there is a conserved energy. And now if we put together the conserved energy with this propagation, then you can see geometrically, if you will, that the wave has to decay like 1 over t. Why is that? Well, imagine that you have energy 1 spread over, well, energy 1 given by your initial disturbance. This energy 1 will typically spread evenly over this shape, right? This shape has what volume? Since this is, say, on the order of 1 in width, this area will be the same as the surface of the 2-sphere of radius t. So it's t squared. So the only way for you to preserve L2, forget the gradient. This is all smooth, right? Gradient is like u squared. So how do you keep this constant? Since you're integrating over volume of size t squared, this has to decay like 1 over t. T squared times 1 over t squared is 1. So you see that things fit together. With this energy, or in dynamics, it's called Hamiltonian, comes a Lagrangian. And this is where the wave equation stops being a model, like the string that is perhaps not super realistic. The Lagrangian is a completely different story, and in physics, Lagrangians are kind of sacrosanct. Think of general relativity, right? So you have a Lagrangian here that might look like a formal object, but it is, I think, it's of fundamental importance. So this, of course, is the Lorentz analog of the Dirichlet energy, right? So the Euclidean model would be ut squared plus grad u squared. The Lorentz invariant analog is this here with the Lorentz signature, and this is an integral over 1 plus d. So we can't minimize this, but we can look for critical points. And if you look for critical points, it would mean that you replace your u by this, and then you take an epsilon derivative, evaluate at epsilon equal to 0, and you integrate in space and time. Imagine now this is not a formal object, but u is, say, smooth and compactly supported, so that everything makes sense. And then you will immediately agree, if you do the calculation in your heads, you integrate by parts once again, you will get box u times phi. So this also shows you that you don't have to assume that u is compactly supported. It's enough if phi is compactly supported, right? And since this is 0, what is a critical point? It means that this vanishes for all phi. So then this has to be 0, and you get your wave equation back. Why is this point of view so fundamental? Because it immediately tells you what a wave is that takes its values in a manifold. If I had asked you, after telling you what D'Alembert wrote down for the string, what is a string taking its value in a manifold? It's an absurd question almost. But when you see the Lagrangian, you know immediately what to do. You replace this by the Euclidean, by the Riemannian length. So the Lagrangian is now, so imagine that you look for U taking Minkowski space into a manifold. It's just a Riemannian manifold with metric G. So then your Lagrangian, of course, is going to be 1/2 UT G squared minus the sum of del JU squared, metric G. And if you now look at the critical points, this answers the question what a wave into a manifold is, because you obtain, so let me be careful here. There are a number of ways to do this, intrinsic, extrinsic, what coordinates do you put on M, etc. Let's assume our M is embedded into some Rn. This again is a Tx integral. So M is embedded into Rn.
Yes.
We write the map U as a column vector. Then L prime is 0 is the same as box U is perpendicular to TUM, in complete analogy to the harmonic map equation, where box becomes Laplace. Now, again, in analogy, you know what to expect. This doesn't look like an equation. What does it mean, box U is perpendicular? Well, the second fundamental form appears. So this becomes, in the extrinsic formulation, this then becomes A, where A takes the second fundamental form, it takes its values in the normal bundle. So A, and where I'm using summation convention, I could also write this differently. I could write beta here, both downstairs, and here I put the Minkowski tensor. So the Minkowski tensor is just minus 1, 1. All right, so let's do a concrete example. If the target is S2, you can also take other dimensions. It can be SD also. So SD minus 1, say, or let me just write SD. And you go from 1 plus D into SD. What does this amount to? Something very beautiful, where this is now a vector with D plus 1 components. This is U, UT squared minus grad U squared. Okay? And U is your position on the sphere, which is identical also to the normal vector to the sphere at the point where you sit. Right? And here you see that this is an nonlinearity that appears intrinsically as expression of the curvature. If your manifold has no curvature, you obtain the flat wave equation. Box U is 0. So the nonlinearity here appears for intrinsic reasons, and it's a very special nonlinearity. It's a so-called null form, but it takes me a little bit too far to explain what a null form is. These null forms have played a huge role, starting with the work of Christodoulou and Kleinemann. So this is the extrinsic form of the wave map. There is also an intrinsic form. I don't want to pay too much attention to it perhaps for now, but it works like this, where this is just a standard derivative you raise. This is Einstein's summation convention with this tensor, with eta, alpha, beta. And this is the covariant derivative on the pullback bundle. When you use the map U to pull the metric of the sphere or the manifold, it can be any manifold, back to Minkowski space. All right?
And if the domain weren't Minkowski space but some other,
then
still the same equation.
Absolutely. So
Which you
and then how do you incorporate this into this Lagrangian? Well, you put the metric of the Minkowski space here, and everything goes automatically. So these wave maps have a very rich theory by now. Unfortunately, it can be very complicated to explain at least the basics of that theory, I have to introduce another notion, namely that of, well, posedness and criticality. So what do we mean by these notions?
As being a
Yes.
solution where X is like a point.
Beautiful question. So, yes, geodesics can be used to write down wave maps. In fact, if you take a geodesic gamma, say manifold is complete into the manifold, and you take a free scalar wave, then the composition, so your wave phi parameterizes the geodesic. This is a wave map, but a very special one. It has a one-dimensional image. So what do we mean by these notions? So, of course, given such a hyperbolic problem, you expect that you want to solve the Cauchy problem, the initial value problem. So what you would assign yourself is you would give initial data. U at time 0 is a fixed, say, smooth map taking values in the manifold. And ut at time 0 is a fixed map taking values in the tangent bundle. This is a vector field, right? And then you ask, so given, so these are smooth, given and smooth, and we can call these creatures U1, U0, U1. Smooth U0, U1. Does there exist a smooth global, meaning for all times, evolution of wave map problem, WM? That's the wave map equation.
Is that what a wave map is? I wondered what that was.
A wave map is a solution if in the extrinsic formulation to this. That's a wave map. So it's the analog of a harmonic map where you replace the Euclidean metric with the Minkowski metric. So the answers here are kind of known, although details are still unknown, especially with regard to the so-called supercritical case. So what does all this mean? The notion of criticality is based on looking at a particular symmetry. It's not an isometry, it's a conformal symmetry, and it's scaling. So it's a big word for just scaling. What you do is you take your wave map U at Tx, and you replace it by U of lambda T lambda x, where lambda is a positive number. And you will see immediately from the equation that you generate another wave map for fixed lambda. So this scaling preserves your structure here, but then you ask which Sobolev spaces are invariant under this scaling. So it's quite natural for reasons I should explain why you look at Sobolev scales of regularity. Why don't you just work with smooth evolution? Well, the reason for this is that it's not easy to quantify and unnatural to this beast to work in the smooth category, because how do you quantify that? But the energy tells you shouldn't really be doing this. You should be looking at L2-based spaces. And so it's very natural to, for example, in the extrinsic formulation with a sphere as target, there can be no question what I mean by this, what I'm about to say, that you take your data in these Sobolev spaces, H dot S. Yeah, what does this mean? It means that U0 has S, doesn't have to be an integer, S derivatives in L2. Okay? And what is that? If U0, U1 are these vectors, that just means that each component can be Fourier transformed. And so this means that integral U0 hat Fourier transform is C squared, absolute psi to the 2s d psi. And similarly for this creature, you have s minus 1 here. This would be the hs norm dot squared of this is finite. Okay? And these spaces are really ideally adapted to this problem. And now you want to know which S is invariant under this type of scaling. Well, you immediately notice that if S is d over 2, then the Jacobian factor, which is lambda to the minus d, is precisely cancelled by this weight, right? So this is S critical. This is this famous scaling exponent here, and the same philosophy, as simple-minded as it may seem, you can apply to any kind of nonlinear hyperbolic or Schrödinger equation, and it has proved to be actually quite accurate in predicting what the well-posedness should be. Do you have a meaningful evolution theory or not? And at least for small times, this makes sense. And so notice the following. The energy has a natural S attached to it. The energy is associated to S equals 1, because it gives you one derivative. So then, what is subcritical? Subcritical means that the scaling number is less than the energy number. So S crit is less than S energy, if you want. We know that's 1. Critical means, of course, equal. So d over 2 equals 1, and supercritical is 3 dimensions and higher. Critical is dimension 2, subcritical is dimension 1. So the logic of supercritical equations is, even if you start with smooth data, which are much better than these numbers, you don't expect a meaningful global flow. And indeed, in the 80s, Jalal Shatta observed that for what I'm about to raise, this very equation with 3, okay, or higher, that you can find an elliptic object, so Q of R over T, and since you're allowed to reverse the error of time, this creature would then blow up at time 0, right? Because you create a
Yeah.
So Shatta, around 87, observed that you can solve the wave map problem for a very special wave map, for maps that are functions depending on a single scalar, R over T. And he obtained Q by solving an elliptic problem. Later it was realized it's just the arctan. Physicists realized that he was just talking about the arctan. So here you can have finite time blow-up. For supercritical problems. For critical problems, so in other words, no global smooth evolutions, because this thing becomes singular when you approach time 0. So critical, meaning d equals 2, it took many years, starting with work of Kleinemann-Macedon, Kleinemann-Selberg, and then Tataru, then Terry Tau, and I will describe other results of more recent nature. Terry Tau wrote a very well-known paper in 2000, where he proved that for small energy, wave maps from 2 plus 1 dimension into, in his case, the sphere, but then Rodniansky, Kleinemann, and others proved this works also for more general manifolds, that you have small data global flow. So the Cauchy problem for wave maps from critical, in critical dimensions, small data global flow. By the way, these results also apply to higher dimensions. What's the logic? Well, supercritical problems, small data, you don't see the supercriticality really. It's only in large data that you see the supercriticality. So Terry Tau's papers and Tataru's papers are in all dimensions. But the critical one stands out because this left the question open: what happens for large data when you don't have small data? D equals 1, the subcritical case was settled many years prior. there you have global evolutions. Cauchy problem has global solutions. So then there were a number of works. Sterbins Tataru. There was Krieger and myself, and there was Terry Tao. All happened around in the summer of 2009. So let me describe Sterbins Tataru. Well, it takes me longer to describe this than to describe what we did. I don't want to be chauvinistic, but so what we did is we looked at the case of Minkowski space 1 plus 2x into H2 into hyperbolic space, which has negative curvature, and we saw that you have global evolution for all data. Sterbins Tataru.
Intuitive reason.
I will get to that in a moment. It will become clear why something like this works because of what I'm about to say with Sterbins Tataru. It's the non-existence of harmonic maps in negative curvature. Okay. And I should have perhaps, before stating these results, stated an earlier result with a sphere S2 where we observed finite time blow-up. So the curvature of the target, the geometry of the target, determines the global flow. So the message here is, sorry if it's a bit contorted, small data and local existence in time is governed by these games with scaling. So you compare the critical to the energy, right? That should answer your small data question. And sure enough, this is what Terry Tao's theorem says about small data. But large data is not answered at all by that. For large data, you have to look more closely, and you need to take the geometry of the target into account. Sterbins Tataru have a beautiful theorem that says that if you map yourself into a compact manifold, two-dimensional manifold,
One complex,
two real.
Two real.
To a Riemann surface.
to a Riemann surface, yes. So if you map to a Riemann surface, I think in their paper they required compact, then you have a dichotomy. If your energy of your initial data, so there is a well-defined notion of energies, again just integration by parts, if it's less than the minimal energy of a non-constant harmonic map, then you have global existence. All right? So in particular for H2, there is no non-constant harmonic map. So for all energies, you have smooth evolutions. The proofs that they used and we used are not identical. They're similarities, but we use the method of concentration compactness, which to some extent has become a mainstream method to address global large data problems in evolution, dispersive evolution equations these days. That's a whole story. I would have to devote several colloquiums so that I can try and attempt in a simpler setting with the time. Okay.
From where to where? You have a 2-1 space.
No.
Two. I see. So reduce
Space
to space. Okay.
And so there are some open questions related to this. You can ask if blow-up, how does blow-up occur? Suppose you take energy slightly bigger than the energy of a non-constant harmonic map. You would expect that blow-up to happen by rescaling of such harmonic map. And I'm about to describe a result of this nature. Terry Tao put a series of papers on the archive, I don't think he's published them yet, where he considers a similar production for harmonic hyperbolic space Hn. Okay? Now, what I just said about the nature of blow-up, yes?
Maps into Hn as the target, or?
Yes, target. Recently, there have also been works, for example, by Andrew Laurie, Sung Jin Oh, and Sorab, who was really very talented young mathematician postdocs. They have changed the metric here, where you put hyperbolic metric on the Euclidean part of Minkowski space. Now, let me describe a little bit of blow-up when your wave map goes into S2. So with Krieger and Tataru, we observed around 2000, when was this? 2006. So here note you have this compact positive curve target, that large data, Terry Tau proved global existence, smooth evolution for small data, but for large data you can construct a blow-up. And the blow-up looks roughly speaking like this, that you go in the so-called equivariant setting. Equivariant setting means here you have a picture of time and R2. SO2 acts by rotation. And here is your wave map into the sphere. And equivariant simply means that this rotation commutes through you. So you can choose to rotate the domain or you choose to rotate the target. What this amounts to, in effect, is that the equation becomes an equation in this angle, the azimuth angle. And if you're curious to see what it looks like, if theta, so this is what the wave map, equivariant wave map, looks like. Okay, so it becomes a much simpler looking equation without derivative terms. If you remember, the second fundamental form had derivative terms in nonlinearity, the null form, which plays a huge role in this theory. By the way, the sad aspect of these developments is they're not simple. So my book with Krieger is a 500-page book, and it has only one proof in it. Okay, and so that's a bit of the sorry state of the field. We don't know how to approach these things more easily. And so why is this? Well, because the dispersion, the decay of the wave coming from here is very weak. Waves decay only like 1/√T. If you try to make global statements about such a hyperbolic PDE, you would want enough decay to make the nonlinearity kind of integrable in time. Right? Isn't it logical? So that's a problem, because the nonlinearity turns out to be quadratic. So then you apply a gauge transform. We just use Coulomb gauge. And with the effect of that Coulomb gauge is that the nonlinearity becomes suddenly cubic. And that allows you get trilinear nonlinearities, but they're kind of messy. And then you have to use, it's not enough to just use Sobolev spaces. You have to use complicated geometry in the Fourier space in Euclidean R2. So you Fourier transform, and you use the geometry of the light cone, which is the characteristic variety where you come from of the wave equation. In other words, you have to understand the wave evolution on the free level, but you have to understand it very finely. And the pioneer who laid the groundwork for the spaces you need is Tataru. Tataru invented a very ingenious class of spaces that take into account, if this is your characteristic variety, remember the symbol of box UTT minus Laplacian. If you Fourier transform this in space and time, you get tau squared minus xi squared. So when you're dividing by box, which is solving the wave equation, you have to divide on the Fourier side by this. That's a problem, because you vanish on the light cone. Tau squared, absolute tau is absolute psi, is the double cone. All right? So how do you divide by something like this? Well, not surprisingly, you will have to keep track quantitatively how close you are to this creature, but that's not enough. You will need to understand the interaction of wave packets. So each slab here on this cone will give rise to a wave, and they interact because they are mixed together in the nonlinearity. So what you need to do, and the worst kinds of interactions are parallel interactions. So you will need to keep track of the angle between different wave packets, and your spaces are in a very quantitative way engineered to take care of these things. So forgive me for getting slightly technical at this point. So to describe our blow-up results is we show that we can construct a blowing up solution of the form harmonic map R over T to some power alpha plus decaying terms. And this is as time tends to 0. And alpha here is a number that we now know can be taken to be bigger than 1. And this is very important because Struve in 2000 showed that unlike Chautard's example, which is the self-similar blow-up, it's still written on top, it is impossible in 2 dimensions, in the critical dimension, to have self-similar blow-up for a wave map problem. What Struve showed is that if you have in the equivariant setting, if you have blow-up of a wave map from 2 + 1 dimensions into S2, then it has to happen through the bubbling off of a harmonic map. But along a series of scalings which are cuspidal, they cannot be self-similar.
R is just the norm of X here?
Yes, yes, sorry.
And so Struve said his result implies you cannot possibly do this with alpha equals 1. And then we came up with a somewhat strange construction that showed that you can actually do that. So in the remaining time that I have, and I'm not sure how much that is, let me go to an easier equation, which is not geometric, but where methods of dynamical systems nicely come into play. So let's go now to a class of equations, and for simplicity, I'll pick a simple nonlinearity, u cubed. I do want here a power, but I wouldn't have to take cube. I just take cube for simplicity. And let's say, but again, this is not so relevant, that we are in. So how does this creature behave? Well, for one thing, you can observe that in analogy, if you want to, with harmonic maps, which are stationary solutions of wave maps, this creature has stationary solutions which are again elliptic objects. So if u of t and x is a function of x alone, then you obtain this elliptic PDE, which is simple by now, it's completely standard. And for simplicity, let's put ourselves in the radial setting. Then it is known, this is work, for example, Walter Strauss, I think in the 70s, showed that such things exist, and Beresticki-Lyons have a widely cited pair of papers from '83 on this. So there exists a unique positive radial solution. This is called the ground state. It has the property that amongst all solutions of this, it minimizes the action. So this is a critical point of something, and it's a critical point of the stationary energy. Right? If you j prime phi equals 0, the Fréchet derivative 0 is exactly the same as star. Okay? But even as simple as this is to this day, since if you want to the 70s, 80s, the following is unknown. Well, Beresticki-Lyons proved that there are infinitely many solutions, so-called nodal solutions. The next one would do this. The next one would have 1 0 crossing and then stay below the line but approach it exponentially fast. Then there is another one that has 2 nodes, 2 0 crossings. Okay? It is not known in the radial setting, of course, only, that these are unique, that there are no others. It is known that there is unique positive solution, and that itself is not easy and has attracted a lot of attention. But by now, this is standard. It was finished in the early 90s. So this would be the first excited state. Now, so you have these elliptic objects, but on the other hand, this equation can have finite time blow-up, and you see this in a slightly strange way. You first seek solutions that don't depend on x. Looks like a crazy thing, but you have an ODE. Now, if you're seeking a solution, say at time capital T, that goes to infinity, but then you can ignore this, all right? and you can solve explicitly v of t would be, I think, this. Did I do this right? I hope so. So quick mental calculation, take a second derivative of this, cube it, you get the same thing. If you throw this back in, you just have to correct with a little O1, and this is a time plus a minus that tends to t. Say t is 1, capital T. So here you have a space-independent solution. You will tell me this is crazy because the solution has infinite energy. So show me a finite energy blow-up solution. That's easy by hyperbolicity. So here is your blow-up time. All you have to do is you draw a backward light cone from there. You truncate these data, which are v at time 0, v dot at time 0, and you multiply them by chi of r, where chi is a smooth cutoff that does this. All right? Then you have compactly supported solutions. You know that there is a local in-time evolution, which agrees with this v inside of here because of finite propagation speed. Right? You have a wave equation. So. And therefore, these data, which are finite energy, blow up before or at time t, because how could they not? All right? So this is interesting because such a simple-looking equation can have blow up in finite time. It has infinitely many stationary elliptic creatures. And not surprisingly, I don't have time to go into details, for small data, the solution exists globally and scatters to a free wave, meaning that at time infinity, it looks like a solution without the nonlinearity in the sense of scattering theory. Right? That's not difficult using technology that's Strichert's estimates, for example.
Equation in 4 space dimensions, I guess there's a criticality that occurs in that dimension.
Very good.
It looks like the Yamabe equation.
Yes. So that's delicate. Because you have to be very careful. We only are treating energy subcritical problems here. Okay, once you, so if you're in 4 dimensions, I forget what's the energy critical exponent. Is it 3 in 4 dimensions? 5? I don't mean 3 in all dimensions. I really mean it here or dimension 2, 1, where this is subcritical. So in all these cases, it's subcritical. The theory I'm about to describe applies to higher dimensions, but only subcritically. Once you're critical, for example, in 3 dimensions, that would mean u to the 5. You have to drop the mass term u. That's a very well-studied equation, perhaps too well-studied. And it actually turns out that for these global in-time questions that I'm about to describe, subcritical is almost harder. We know less about them, and the current technology doesn't really grip. Okay? So we have small data global existence for small data. So it's a very natural question. Is there a criterion that would tell you, if you give me data, can I read from the data what the long-term evolution will do? Will it blow up in finite time like these solutions we constructed? Or does it scatter to one of the elliptic objects? What does it do? So Payne and Satchinger found a very partial but nonetheless beautiful criterion a long time ago, 1975. That was before really dispersive theory took off. There were no Strichert's estimates at the time. What they observed is, so their paper is a beautiful paper in the Israel Journal. They came from a very physical way of thinking. They noted the following thing, that if you take your initial data, U0, U1, and if these data have energy less than the energy of the ground state, then there is a dichotomy. There is the so-called Nehari functional. If this number is the dichotomy greater or equal 0, you have global existence. If it's less than 0, you have finite time blow-up. Where does this come from? Well, what they looked at is they looked again at this action J. You can call this action, you can call it stationary energy. And they considered a symmetry, which again is dilation symmetry, but this time in the dependent variable. So And because I want this to be a group, I don't call it lambda anymore, I call it e to the lambda. And if you now differentiate in this symmetry, then you obtain precisely this functional k of phi. So what's the logic behind this? What is the logic that says that the sign of this derivative, right, under this conformal symmetry, should decide the fate of your solution? And their argument, if you read their paper, they explain it really in physical terms. So draw this graph. Take phi to be not zero. Draw the graph of the stationary energy of the dilated phi as a function of lambda. When lambda tends to minus infinity, the quadratic will beat the quartic, and it will look convex. Over lunch, we said there is another idea, convex, concave. So, whereas when lambda is large and positive, this will beat the quadratic, so it looks like this. And it has a unique place with a horizontal tangent. But now you have to gauge yourself into some kind of normal situation. So you move the horizontal tangent to lambda equals 0, right? So it's like a gauge freedom you have. So you require that the horizontal tangent k equals 0. This is precisely k of phi equals 0 then, right? Because look at this. So what's the logic to them back in 75 that you should have global existence? Well, it's the trapping here. It's like a well that traps the solution. But this height should be the critical height. But what does it mean? This height depends on phi. So what you should be looking at is the inf of j of phi when phi is not 0 and k of phi is 0. Do you agree? This is the shortest path over which the solution could escape. And what do you expect this to be? Well, you set up the Lagrange multiplier problem associated to this variational thing, and you see q and minus q are the unique minimizers. All right? So therefore, if you're here, which means k is greater or equals 0, you're trapped by the well. If you're here, you use a convexity argument, an indirect one, which is clever. You have to look at the L2 norm of the solution squared, and you differentiate it twice, and you see that it's concave, but it can't be, because then it would have to cross the axis, but integral u squared is always positive. So by this contradiction argument, you then see that here you have finite time blow-up. So this was the state of affairs until 75.
So the conclusion here is independent of the time derivative at the
Correct. And since I'm running out of oil, let me describe very quickly. In 2010, Nakanishi and I proved the following theorem that allows the energy to be slightly bigger. So if the energy of your data is less than the energy of plus epsilon, where epsilon is a suitable small number, then you have the following picture. Here is a ball in phase space, in H1 cross L2, infinite dimensions. There exists a codimension 1 smooth manifold. And this is a small ball, so of radius. Well, this is my radius here, like epsilon. Small ball. So if you start above this manifold, you have finite time blow-ups on one side. Below, you have global existence and scattering to the vacuum to 0. And if you start on this codimension 1 manifold, you exist globally in forward time, and you scatter to Q, meaning that any excess energy that you give your data at time 0 radiates off to infinity. And if you look on a computer, which is very hard to do because with probability 0 you hit this manifold, so you have to look very carefully with numerically. But you will really see that the formation of this Q from magic, by magic. The solution somehow knows that it suddenly should become Q. This is in forward time. If you reverse time, you get another manifold which is transverse to this, and on either side you have this behavior in negative time. So you have 9 sets, 4 open, then the 4 leaves, and then the intersection. In the language of dynamical systems, this is the center stable manifold, because the linearization about Q turns out to be hyperbolic. You have to prove that it's hyperbolic. So you can use the language at least. This is the center stable manifold. You can use the Lyapunov-Perron method, for example, to construct invariant manifolds. You have this picture. In fact, our theorem doesn't just apply in a neighborhood of this point. It applies in the whole set of data when the energy is just slightly above that. And for this, it's not a perturbative argument. Why? Because here you have an unstable manifold. So you have exponential dynamics. Here it's one-dimensional because the linearized operator about the soliton, which is this Schrödinger operator H, is this. And then you show that the spectrum looks like this. It has a unique negative eigenvalue, and then continuous spectrum here, nothing here. This can be extremely difficult to determine the spectrum because this is not completely integrable. And this one negative eigenvalue gives rise to a unique one-dimensional stable manifold, unstable, sorry, here you have this one-dimensional stable manifold. And so what if you get pushed out of this? You spend a long time outside, can you come back in? So we have to prove the absence of such homoclinic orbits, or near homoclinic orbits, to prove that theorem. But it is wide open to remove this epsilon. If you go to the critical equation you asked about, so in 3 dimensions u to the 5, then there is an understanding using completely different methods. This is a result, a very beautiful result, just a few years old, 3 maybe, by Deukert, Koenig, and Mell. Let me not go there. Let me just say that for the case of slight dissipation, so when you add, this is a theorem from 2010 with Nakanishi. If you add slight dissipation, which is this here, to this problem, and let's again be in 3 dimensions with u cubed, but the theorem is much more general. We can allow f of u. Energy is subcritical, however. And alpha is positive, then the energy becomes a Lyapunov functional, but the Lyapunov functional has an indefinite sign. It's not positive definite. So Nicolas Burck, Geneviève Rogel, in Orsay in France, and myself in a week, hopefully or 2, will put a paper on the archive where we give a complete description of the dynamics here. Alpha can be as small as you wish. We say that either finite time blow-up or convergence, because of the dissipation, you don't talk about scattering anymore. You can actually converge strongly in the energy topology. Convergence to a stationary solution. And this stationary solution may be 0. So no restrictions on the energy. And this uses invariant manifold theory. So this is an example. So I'm excited about this. Why? Because we actually use papers from the dynamics literature. We use a paper by Brunowski-Polachik, a convergence theorem in infinite dimensions, Banach spaces. The issue becomes this. To prove this, we show that if you take any data, then there's either you blow up finite time, then we do nothing, or you have a global evolution. It was not known in this class of generality that there is a global trajectory necessarily bounded. Not known. In fact, we don't give a separate argument for this. We deduce it after the fact from this convergence. Right? If you have this convergence that's stationary, then of course every global trajectory has to be bounded. But then we look at the omega limit set of the trajectory, and we find there is an equilibrium in this omega limit set. We linearize about this equilibrium, which has to be a stationary solution. To get this equilibrium, it's very useful to use the energy, which is a Lyapunov functional. Then you have to use a convergence theorem to show that the full trajectory converges to this equilibrium. And for that, you use a result of Brunowski-Polachik that says if you have a center manifold, which we might have here, but it's only one-dimensional, you have an unstable manifold coming from the negative eigenvalues of the linearized guy, and we have a huge amount of stable spectrum, stable manifold. Then if the center manifold is stable in the Lyapunov sense, orbital sense, and if your trajectory does not converge to the equilibrium in the limit set, then it has to, the omega limit set has to contain a point in the unstable manifold, which is very natural. And that gives you a contradiction, because this would have to be an equilibrium. But you can't have an equilibrium in the unstable manifold. So that finishes there. Okay, thank you.
What's known about long-time existence? If you look at wave maps from, let's say, the simplest case, maybe a two-dimensional Riemannian manifold times R, make the Lorentz product, and look at that map into
that generality. So Laurie, in one of the things he did in his PhD at Chicago, he took 4 plus one-dimensional Minkowski space, and he took a metric that decays nicely at infinity. So near Euclidean, but it's allowed to be a big, but no, still small perturbation here. But at infinity, it really has to decay. Think of a compactly supported small perturbation of Euclidean metric. And then he showed a theorem in the spirit of Totaro and Tau, following Shatar-Struve, which I should have mentioned when I rattled off the names for small data global existence. For technical reasons, it needs to be in 4 plus 1 dimension. He shows that if you do a slight perturbation of the flat Minkowski, then you still have small data global existence. And that uses Coulomb gauge, it uses the method of moving frames. So he takes the derivative of the wave and formulates it in terms of a moving frame and Coulomb gauges.
Is it because you need the scaling structure to some extent?
Need what to do the scaling structure? You mean that you
I asked you about the domain space being a more general Riemannian manifold.
the domain space, right? Yeah. Instead of Minkowski, you replace it with a manifold.
Some Riemannian manifold cross R, so it's the simplest case. But
there should still be a scaling
in the time.
Because you can compare it to Euclidean space by zooming in, and things look very Euclidean on a small scale.
Absolutely. So if you have blow-up in such a setting, the blow-up should look exactly like the Euclidean one, and such results exist. For example, Sorup, Shoshahani proved in his PhD in Lausanne with Krieger that to get blow-up from the sphere to the sphere, you can do this using the Euclidean construction, not surprisingly, right? Because when you have blow-up, the manifold looks flat. But if there are many challenges with replacing the domain, the Minkowski space, with a very general creature. And that has to do, think classically. You replace free Newtonian trajectory, put a particle into a potential, right? Think of quantum mechanics. What is this? You have like these Schrödinger operators I keep writing down. You put a particle into a potential. Well, it can get trapped, right? But it can also scatter. So classical scattering theory is just here. You have a free Newtonian trajectory. Here's your Potel trajectory. At time infinity, you want them to look comparable, right? If you start messing with the metric in such a way, for example, take a periodic perturbation of the metric, crazy things can happen.
Is that why the hyperbolic metric?
The hyperbolic metric is a whole different story. That's because of actually the explicit formulas you have. Because how do you understand the free wave on a hyperbolic metric? How do you remember the Huygens Principle? Actually, the Huygens Principle is very unstable. The sharp, not the general Huygens, but if you even breathe at the sharp Huygens Principle, which says that the wave lives on the boundary of a cone, it breaks down. You will have a tail. The wave will have remnants inside of the cone. This is what happens in hyperbolic space. You have tails. And you have to first understand the whole free theory, using the distorted Fourier, using the Fourier transform perhaps on hyperbolic space, using some explicit parametrices, some solution formulas. So the state of the art is this. Either you have a rigid setting like hyperbolic space, symmetric space, something where you have explicit representation formulas. They can look extremely complicated and hard to analyze. Or you do perturbations of something that you understand. So at this point, nobody has done, I think, perturbations of hyperbolic. Perturbations of Euclidean. Totaro, for example, one of several, and it's all very complicated. Totaro uses the FBI transform, it has a funny name. The FBI transform, you work in phase space. Coherent states, you have to use machinery, analytical machinery, to get your hands on the free evolution.
Thank you very much again.